Alright, gang, here we go. Chem 2, Unit 11. We're going to start putting together the pieces of what we've been after all along. How do we use Gibbs free energy, entropy, and enthalpy in order to determine whether or not a given reaction will be spontaneous? So, last time we talked about Gibbs free energy and we learned the following formula. Actually, they give it to us right here. We learned this formula. Delta G is equal to delta H minus T delta S. We also know that if delta G is negative, our reaction is spontaneous. If delta G is positive, our reaction is non-spontaneous. So looking at these different values, we can get an idea of whether or not something is going to be spontaneous or non-spontaneous right away. So look at this. So if our reaction is negative, remember this means it's exothermic, and our entropy is increasing, okay, this gives us a negative T delta S, right? Because T delta S is negative, or is subtracting from your delta H. That means no matter what your temperature value is, your delta G will always be spontaneous. Therefore, he's spontaneous at all temperatures. All right, let's look at this next one. So this guy here, positive enthalpy, so that would be an endothermic reaction, and our entropy is decreasing. So no matter what our temperature value is, because this is positive and this will make this positive, our delta G will always be positive, so therefore this is non-spontaneous at all temperatures. Okay. So these two are exact opposites, and notice that their examples that they chose are the exact opposite from one another. The forward and the reverse reaction of the same thing. All right. Next guy here. So now we've got an exothermic reaction, but the entropy is decreasing, right? Entropy is decreasing. So if entropy is decreasing, that makes this positive. So therefore, if we look at our graph here, we could have a positive delta G or a negative delta G. It depends on how big that temperature is. If our temperature is too high, then the positive portion will be bigger than the negative portion of this equation, and therefore you will end up with a positive delta G. Or if your temperature is low enough, then this part will not be able to overcome the exothermic reaction part, the negative delta H, and therefore you will have a spontaneous reaction. So this reaction, okay, it would be spontaneous at low temperatures and non-spontaneous at high temperatures. And they're giving this example here of this phase change, which really makes sense, right? If you're at low temperatures, okay, then you would spontaneously freeze. But if you're at high temperatures, then you would not spontaneously freeze. Okay, next guy here, we've got a endothermic reaction, right? Endothermic reaction, and then but an increasing entropy. Okay, so overall this will be negative. So if we plug those guys in, we can see that once again we could get positive or negative. It depends on how big that temperature is. So this turns out that if the positive nature of our entropy has a big enough effect, meaning that we have a high temperature, will end up being spontaneous. At low temperatures will be non-spontaneous, right? So you got to kind of look at each of these four things here in order to determine what's going to happen. So it takes a little bit of practice, a little bit of getting used to. One thing that I like to do is, like, if I'm confused by looking at it, I'll just plug in a value. I'll just pick a 1 and -1, or a -1, and just plug those in for my delta H and delta S, and then play around with the temperature to figure out if I can't quite, like, if I'm having a little of a brain fart moment and I can't remember what that relationship is. All right, so delta G does change with temperatures. Okay, and so the magnitude of that temperature actually does matter to whether or not our reaction is going to be spontaneous, especially if it's an exothermic reaction with a decreasing entropy or an endothermic reaction with increasing entropy. All right, so let's do a practice problem here. It says we used Hess's law to calculate delta H for the combustion of propane at 298 Kelvin. So there's the combustion. We calculated that as negative 2,220 kilojoules. And it says part A says without using data from Appendix C. Okay, so without using data from Appendix C, essentially says no calculations is what it's saying. We want to predict whether or not delta G for this reaction is more negative or less negative than delta H. So let's see, delta G is equal to delta H. That's not an H at all. That's on its way to being a T. delta H minus T delta S. All right, so let's take a gander here. So we got delta H, and our delta H is negative, right? Delta H is negative, and our T delta S. So let's think. So we really got to determine whether our symbol for our S would be positive or negative. So this has 6 moles of gas over here. We got 6 moles of gas on the reactant side, and we've got 3 moles of gas on the product side and 4 moles of liquid. So our entropy is probably going to be decreasing. Our entropy is going to be decreasing. So that means we're going to get a negative value here. A negative value. Which means this guy's going to end up being positive. So we're going to get a negative plus some value, right? Negative value plus some value. So that means this will be, we're going to say delta G should end up being less negative than delta H, right? Because we're going to, no matter what, unless we're at absolute zero, we're always going to be adding some value to it, right? And if we get to a high enough temperature, then our delta G will end up actually being positive, all right? So part B asks us to actually calculate it. So here we've already got delta G, well, we've already got, calculate delta G star. Okay, so we've already got, well, we don't have a way to calculate entropy. We'll just look up. So you could do it one or two ways. You could you could look up your delta S values and do standard entropy of formations, or standard entropies, and do products minus reactants, and then plug it into this formula. But that's twice as much work. Or you can use the delta G of formations, right? So we'll just do it that way. So we'll just say delta G of formations, and so we'll take products minus reactants. So this would be 3 times CO2 plus 4 times H2O, and this would be minus 1 times C3H8 plus 5 times O2. Alright, so that means our delta G star is equal to 3 times, and I looked these up earlier so I didn't have to look them up now, negative 394.4 plus 4 times H2O was negative 237.13 minus 1 times negative 23.47 plus 5 times 0, because O2 is standard. So, and delta G, let's see, 3 times negative 394.4 plus 4 times negative 237.13 minus 1 times negative 23.47. So I got negative 2108. And again, this would be kilojoules. Alright, so yeah, it is less negative. We were right. Yay us. Yay us. Alright. Okay, so this guy here says, it says if a reaction is exothermic and its temperature change, okay, and its entropy is exothermic and its entropy change is positive, which statement is true? So let's see. So delta G equals delta H minus T delta S. Okay. So we've got a entropy change. No, exothermic, so that means this guy's negative. He's negative, minus T times some positive value, right? Well, so entropy change is positive, so that means no matter what we do, we'll get a negative value. Delta G is always going to be negative. This reaction is spontaneous at all temperatures. The reaction is non-spontaneous at all temperatures. That's the exact opposite. The reaction is spontaneous only at high or only at low. Well, it's got to be A, right? Because we'll be negative no matter what. Let's see. Let's try this one. It says for the combustion of butane, this guy here, do you expect delta G to be more or less negative? So combustion is always going to have a negative delta H. So essentially we just have to ask ourselves, is our entropy going to be increasing or decreasing? So here we've got 15 moles of gas. 15, right? 2 from this guy, 13 from this guy, and they're going to make 18 moles of gas. So your entropy is going to be increasing, so therefore he will be more negative. Delta G will be more negative. All right. So this guy here, let's see. We're just doing a whole bunch of practice problems because this is kind of where the rubber meets the road a little bit on all kind of like this whole unit. So it's the Haber process for the production of ammonia is that guy. For this reaction, our delta H is negative. So here's some important values. Our delta H is negative 92.38, and our delta S is negative 198.3. Notice the units. Assume delta H and delta S don't change with temperature. That's very nice of them. Predict the direction in which delta G for the reaction changes with temperature. So we've got a negative entropy, but it's exothermic. So remember, so let's think here. So A, we're going to write it out again because we're trying to memorize it. Delta G equals delta H minus T delta S, right? So if this is negative, but this is negative, that means this is going to be positive, right? So as our temperature goes up, our delta G is going to become less negative, all right, or more positive. So as temperature goes up, delta G goes up, right? Cool. Yep. All right, part B. Says calculate delta G at 25 degrees and 500. So we're going to double check our work here. So delta G, so we'll say at 25. So here's 25 degrees Celsius. This is 298 because we always got to have it in Kelvin, right? So delta G would be equal to delta H. So that's our negative 92.38 minus our temperature value, 298, times our delta S, which would be negative 1.1983. Now remember, you have to convert it to kilojoules because delta H is in kilojoules. So we have negative 92.38 plus 298 times 198.1983. And I get negative 33.3 kilojoules. All right, so now what about at 500 degrees Celsius? So that would be 273, so 773.15 Kelvin. All right, so our delta G would be equal to negative 92.38 minus 773.15 Kelvin times our same entropy value, negative 0.1983. So we say negative 92.38 plus 773 times 0.1983, and I got 60.9 kilojoules. All right. So we were right. So as temperature went up, our entropy also, or our Gibbs free energy also increased. So notice that below that 25, it was spontaneous, and above 500, at 500, it was non-spontaneous. So somewhere in the middle of those, it became non-spontaneous. All right. It says, what is the temperature above which the Haber ammonia process becomes non-spontaneous? Oh, so we're actually going to calculate that value. So delta G is equal to delta H minus T delta S. Now, if we're looking for we're at the point at which where it above becomes non-spontaneous, essentially we want to know, well, where does this equal 0? So 0 is equal to delta H minus T delta S. So we can just solve for that guy then. So that would be, so add that to both sides. So T delta S is equal to delta H. So that means our temperature we're looking for is when delta H over delta S. So our delta H value, we'll see, I should have written these down. Delta H was negative 92.38. Delta S was negative 0.1983. All right, so 92.38 divided by 0.1983, and so that happened at 466 Kelvin. Well, both those have 4 significance. So we'll say 465.9 Kelvin is where that occurred. All right. So 465.9. Oh, frickin'. I put it in Celsius. I was like, I'm really worried. So now we got to subtract 273.15. So 192.7, which is our 193. Why would they do that to me? I don't know. All right, here we go. Next problem. It says write out the equation that defines the normal boiling point of liquid carbon tetrachloride. All right, so that's pretty easy, right? So the equation that defines that, well, that would just be carbon tetrachloride liquid in equilibrium with carbon tetrachloride gas, because it's the boiling. All right. And it says, what is the value for delta G for the equilibrium? Well, that's something we just defined when we talked about that. So when you're at equilibrium, your delta G is equal to 0. All right. Use data from Appendix C and equation 19.12 to estimate the normal boiling point. All right. So the normal boiling point would be when. This is actually just very, very similar to the problem we just did. So this is good practice. So delta H minus T delta S. All right. So this is the same idea. So we can rearrange. This would be 0 is equal to delta H minus T delta S. All right. So that means our T is, and I'm going to skip a step here because we just derived this delta H over delta S. So that means I just got to calculate delta H and delta S. All right. So let me pull up the appendix from the textbook. The appendix. So here we go. Here we go. So we got products minus reactants. So it would be 1 times our CCl4 value, which is negative 106.7, and then minus the react. So products minus the reactants. So 1 times the CCl4 negative, so that'd be negative 139.3. And then on the bottom, and I got to remember to divide all these by 1,000, so this would be 1 times 0.3094 minus 1 times 0.2144. All right, and let's see what we get. So we have in the numerator, we'd have negative 106.7 minus a negative 139.3. So I got 32.6 on the top. And on the bottom, we'd have 0.3094 minus 0.2144. So I got 0.095. And when we divide that, so we say 32.6 divided by 0.095, we get 343 Kelvin. So that it would be the normal boiling point. So notice that we can use, it's kind of crazy, we can use those values to actually get a good idea, actually a really solid idea of where the boiling point is. All right, I'm pretty sure that that's it. And oh, we could even double check. Did we get the same thing they did? Well, we don't know. Oh, here we go. We did 343 Kelvin. Look at that. All right, so that's it. Hope you're having a great time. You're learning thermodynamics. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.